Okay, hi, hello again. And today I'd like to talk with you about transformers. And these are not those toy robots that turn into monster machines. These are devices used in electronics and electrical circuits in order to transform, change voltages, currents, and we'll discuss it today, impedances. So there's an interesting physical situation that occurs when you take a conductor. So let's take a conductor and let's put a plus and a minus here. When you move charge, so we talk about current, it moves, for example, in this direction from positive to negative. Or some people talk about electrical movements, and that's fine. We can even do that as well, all right? So let me just do this for a second. Let's just clean this up a little. Okay. And we can, so electrons move from minus to plus, charge current moves from plus to minus. Now, if you've got current moving, for example, let's look at the end of this conductor. If we look at that, and here it's coming at you, and we use our right hand, and we put the right hand, so it's coming at me. We put the right hand thumb in the direction of the current. What you'll notice is your fingers will curl in a direction of a magnetic field. Okay. So you're saying, okay, but is that the same for electron flow? Electron flow does the same thing, except what you do is you use your left hand. So if we look at the flow, because it's leaving us, I'm going to show it like this, and I use my left hand, my thumb pointing to you, guess what? My fingers also curl in the same direction of the magnetic field. So the magnetic field, whether it's formed in your mind by current flow or electron flow, the magnetic field will still be in the same direction. Now, the interesting thing is we're just moving charge here. The other aspect of magnetic fields and current or electron flow is that if a magnetic field cuts this conductor, so if we have a magnetic field cut this conductor, we will actually cause charge to flow in that conductor or electrons to flow in the other direction, what have you. So there's an interesting relationship between charge moving and a magnetic field being formed, and then vice versa, a magnetic field cutting a conductor and the charge being required to move as a result of that magnetic field. It's a very tight interaction between these two physical phenomena. Now, the property that we describe in being able to create a magnetic field by moving charge is the property of the conductor is called inductance. And inductance is signified by the symbol L. And the units for inductance are henries. So we measure inductance in henries. And the symbol for henries is H. So we notice that there's a situation that arises here. Okay, what can we do with this? What can we do with this? We've got a long length of wire. We push a charge through it. We can create a magnetic field. We know that if we have a magnetic field moving and we have, say, a long length of wire, we should be able to move a lot of charge as well. So why don't we create a device? Why don't we build a device here? And what I'm going to do is I'm going to take a lot of wire and I'm going to coil it up. Why? Because I want to stay tight with my device. So if I coil it up, I can make it occupy a very small space. And I'm going to push, in a second, I'm going to push a changing current through this coil of wire. Here, this is a direct current. It's just going in one direction. What I want to do is put a changing current through this device. So I want to, as well, I don't want the magnetic field just to be out where it wants to be. I'd like to concentrate it. So what I'm going to do is I'm going to wrap these wires around an iron core, a type of toroid, a bobbin, let's say. And on the other side, then, I'll wrap a smaller set of wires, in this case here, fewer turns, on this device. So I've got more turns, fewer turns. Now, what I need to do is, it's one thing to set up the field and it stays there, but I need to cut the other side of these turns here with my magnetic field, which means what I'm required to put in here is an alternating signal, okay? AC signal. It's like we're going to take our charge and we're going to move it, and then we're going to slow down, and we're going to reverse direction, and then we're going to slow down, and I'm going to move it again, and one more time, I'm going to do this. So this is, I'm going to put a lot more charge in. There it is. It's bubbling out, and then I slow down, and then here I'm going to put more charge in. Okay, let's bubble out, and then slow down, and back and forth. So I represented this as a voltage changing in time, in amplitude, and a time scale here. All right? All right, so what's going to happen? We're going to, right-hand rule if you want to do plus and minus, or left-hand rule if you want to do minus to plus, you're going to create a magnetic field that is going to cut this secondary turn. So this side of this device, which is a transformer, we call these primary. So this is our primary side, P-R-I, primary, and this secondary. Okay, so we have our primary turns and we have our secondary turns. And there is a relationship between this signal that I'm putting in and this signal that I'm going to take out. In fact, if I look with the oscilloscope, and this is my signal here, what I'm going to see on this side is something like this. Okay? Now, you see this is smaller than this. From a voltage perspective, the amplitude here is smaller. All right? And that is because I have fewer turns in my secondary to my primary. I could flip this around. I could make this my primary, this my secondary, and then I'd have a small signal going in and a big signal coming out. Now, the thing about in and out on these devices is that the energy in this world is finite. We cannot create anything or destroy anything. We can only change its format, maybe light into heat and such. So if we look on this side here, then our power on our primary side is equal to our V primary times the I primary. Power is V times I. And therefore, this also has to equal power in the secondary, which is V secondary, I secondary. Now, here's an interesting thing. If I use this configuration here, my voltage will go down. If my voltage goes down and this side power has to equal this side power, primary has to equal secondary, what's going to happen is my current will go up to compensate. Power in the secondary, power in the primary have to be the same, which is an interesting thing now because if we look at the voltage in the secondary, so here, if we look at our voltage in our secondary and we divide that by the voltage in the primary, it's the same as saying that you had the secondary turns ratio divided by the primary. So in this case here, this is a, let's say, a 2-to-1 step-down transformer. You can calculate how much you'll step down by measuring the voltage in the secondary, dividing by the voltage in the primary, and it's the same as the turns ratio. Now, not always present to you in a data sheet, and we'll show you a data sheet in a minute, is the actual turns ratio that way. There's another way of determining turns ratio. If we go back to our inductance side here, the fact that I'm trying to create a magnetic field, this inductance causes a small problem in just how fast the charge can move. I can put the voltage there, but the charge can't move right away because it's somewhat pushing to create this magnetic field. And that concept is called reactance. So reactance is the pushback of the current with respect to the voltage that's applied. If we actually showed on a scope the difference between the two, or in a phasor diagram, we see that the voltage is leading the current. So the current will catch up, and but the voltage will always be in front of it as we continue to change it back and forth, back and forth. Now, that is reactance. But there's another concept because this winding too, as will this one, have a small, very small, but will have a small resistance in it. All right? And by the way, just to clarify something, these two are separate. There is no electrical connection between the primary side and the secondary side. Putting an ohm meter across here will show you an infinite or open circuit. We're coupling our signal as a result of changing an electrical field to a magnetic field back to an electrical field. So let's get back here, because like I said, not all data sheets will give you turns ratios. So reactance is the pushback to the current flow when the voltage is applied. And in this case here we have resistance. This is pure play resistance. Secondary resistance, primary resistance. So the entire circuit pushing back on what we're trying to apply, that is called impedance. And we denote that with the letter Z, okay? Impedance. Now, if we actually then look at a data sheet, more often than not, they will give you the impedance at some fixed frequency of this primary circuit and the impedance of the secondary circuit at that same fixed frequency. And so if we do this, if we take the impedance of the primary and divide it by the impedance of the secondary, we will also get then our turns ratio, our primary to secondary turns ratio. Okay, so that's another way of calculating. Now notice this is slightly different. Okay, this is secondary or primary. That's this way. This is reversed as far as the impedance, as far as what's in the numerator and the denominator. Okay, so that's it. So a reactance plus resistance is impedance, also measured in ohms in both cases here. And because the voltage is leading the current in the inductor, this is known as an inductor, but in the resistor, the voltage and the current are in the same phase, okay, for the resistance. Then in order to calculate the two, and we won't spend much time on it here, what we do is we say the impedance is equal to the square root of the sum of the squares of the resistance and the reactance. But again, I'm not really trying to cover that today. What I'm trying to explain to you is this connection from one side of a magnetic circuit, electromagnetic circuit, to the other side. One last point before I leave this. Normally the manufacturer will put what is called a phasing dot on there, which means that if it's going up here, the signal on the primary, it'll go up on the secondary. If you reverse your leads, what you'll find is the signal will be 180 degrees out of phase, okay? So this is showing in phase, this is showing out of phase. I think we've got it.